So thank you very much, Cynthia, for coming, and please take it away.
Thank you very much. Hopefully everyone can hear me. Great. It's a very nice introduction. It's good to be slow in the technology, to stretch it out. Yeah, so I'm a mathematician, so this will be a much more theoretical theory talk than the one before. It's a real honor to come and speak at this event, and I feel like it's done a really great showcase of how open and how broad the research in theoretical computer science is. So I'm going to talk about some research that I got into during a semester at the Simons program. This is joint work with Nima Anari, Klipi Liu, Cheyenne Oveskaran, and Jun Vuong. Please feel free to ask questions at any point. So for me, this really started in fall 2017 when there was a very large, so both programs at the Simons Institute were the same, and they were on bridging continuous and discrete optimization. So there was a huge number of people there that semester. And at the same time, I'm sorry to advertise also another institute, but in this case, it was really a case of synergy. There was also at MSRI in Berkeley, there was a program on geometric and topological combinatorics. And so you had a lot of people all in the same place thinking about some of the same objects from very different viewpoints. And it was really amazing. And I think some of the stuff I'm going to talk about today, wouldn't have happened as quickly without all of these people being in the same place, and really without the Simons Institute. And some of the work in this was followed up on 2 years later on a program of the geometry of polynomials and implications for approximation algorithms and computer science. So in terms of content, I wanted to warm up to the geometry of polynomials with a simple example. The geometry of polynomials is using properties of real polynomials as functions to try and understand and study various algorithms and combinatorial structures. So as a warm-up, I want to just consider univariate polynomials with real coefficients having the special property that all of their roots are real. So a polynomial of degree d will have d roots counted with multiplicity. I want all of those to be real numbers. And these polynomials appear in a lot of natural places and have a lot of nice consequence. One nice consequence of such a property of real rootedness of polynomials is that if you have is something called Newton's inequalities, which is inequalities on the coefficients of those polynomials. You get some information about the shape of the coefficients. So if you have a real rooted polynomial and all of its coefficients are non-negative, then this sequence of coefficients is what's called ultra-log-concave. So has a shape related to the binomial coefficients. Another consequence is another type of log-concavity, which is log-concavity as a function. So you can check just by a calculation that if you have a real rooted univariate polynomial with non-negative coefficients, and then you do the calculus exercise, then as a function on the positive real line, it is log-concave. The second derivative of the log is negative. And both of these, as hopefully we'll be convinced of by the end of the talk, are interesting and useful consequences that one gets from knowing something about some polynomial. I realize I have no clock up here, so maybe you can warn me. You'll drag me off there, great. So this seems like a toy example, but actually one can derive quite a lot starting from this toy example and going forwards. There are multivariate versions of this. Feel free to ignore the details, but if you have a multivariate polynomial, we call it stable if it has no zeros in the product of the upper half plane. So all of whose imaginary parts are positive. This is something that was developed in solutions of partial differential equations, and then it has appeared in lots of different areas of mathematics and been useful since then. One, sort of canonical example of this is taking a determinant of a linear matrix where the coefficients of the variables are positive semi-definite matrices. The running example, my running example for today is a special case of this, which is going to be the generating polynomial for the spanning trees of a graph. So if you take a graph like this one, and you have n edges, where here n is 5, there's some collection of spanning trees, which I'm going to consider as subsets of the edges that reach every vertex and have no cycles. And you could write down a polynomial here in 5 variables that corresponds to this, which is just to every spanning tree you associate the product of the corresponding monomial. So for example, 1, 2, 3 gets x1, x2, x3, and you sum up all over them. Okay. And by a weighted version of the matrix tree theorem, this is actually a determinant of exactly this form. And so this polynomial has this property, this thing we're associating to a combinatorial object. This polynomial has this complex analytic property of having no zeros in some portion of the complex plane. Okay, which could just be nice, but turns out to be useful and can tell us something about, for example, the spanning trees of a graph. That's the point. So these have appeared in various ways in theoretical computer science. This is not a complete list, but this is at least hopefully a representative sample. So for example, in the late 1990s, early 2000s, these were used as a theoretical tool for various types of convex optimization problems that generalize linear programming and semi-definite programming. So this was sort of pioneered by Goler, and Jim Renegar really sort of pushed the theory to the state of the art, where to such a polynomial one can associate a convex cone and do linear optimization over this convex cone very quickly. And the feature that makes these algorithms work well is exactly this real rootedness property, which is somewhat remarkable. In 2013, in a series of papers, Adam Marcus, Dan Spielman, and Nikhil Srivastava used stable polynomials to answer some long-standing open questions in operator theory and also combinatorics using what's called interlacing families. Particularly, they solved what's called the Cadison-Singer conjecture and gave methods for constructing Ramanujan graphs. And again, one of the things underlying this work was a study of real rooted polynomials and their multivariate generalization. And then one of the other things that was developing around the same time was applications in understanding discrete probability distributions. Counting and sampling from discrete distributions and this notion of negative dependence. Leonid Gurvitz used stable polynomials to bound associated to the permanent of a matrix to resolve something called the van der Waals conjecture about the permanent of a doubly stochastic matrix. And then people also started using these, in particular some of my co-authors, around the same time to develop algorithms for sampling from discrete probability distributions that one would associate to these polynomials, namely the coefficients of these polynomials. And part of the machinery surrounding this is in this beautiful paper by Bartea, Brendan, and Liggett that this class of polynomials captures very beautifully a notion of negative dependence, and one can use sort of this theory of polynomials to really understand operations on probability distributions that are preserved under this. And so because we understand a lot about polynomials, we can then translate that into many things about probability distributions. And so this was what was going on around 2017. And so when we had all of these many people here, including many of the people on this list, we had a reading group on stable polynomials and their various appearances, where people from these different groups started talking to each other and trying to understand what everyone was doing. And that is, and we, for a whole semester we did this while many other things were going on in Berkeley. And this really comes out from that. So just as an example, I can sneak some math in. So one of the properties of stable polynomials is that a certain other polynomial that one can get from applying differential operators is non-negative. And for example, if you evaluate this function here at a point, namely the all ones vector, it tells you something actually about the probabilities of various elements appearing in a randomly chosen subset. So the setup is you're choosing a random subset of the numbers 1 through n, and you have maybe your two favorite elements, I and j, and you want to understand what's the likelihood that they show up and how those likelihoods relate to each other. And what this says is that if your distribution corresponded to a polynomial with this property, then those probabilities that your two favorite elements show up, it's less likely that they both show up than it would be if they're independent. So for example, if we take this graph and we choose a spanning tree of this graph uniformly at random, there's 8 of them. And our two favorite edges are 1 and 2, then the probability that both show up is 2 out of 8, which is less than the probability, the product of the probabilities that they each show up individually. And so this is negative dependence. And it's a property that also is desirable for a lot of sampling algorithms, is that it tends to, if you sample from distributions with this property, it tends to increase the diversity of your solutions. So this is, it's a nice property to work with. One gets it from, guarantees of it from stability, and it's desirable for various sampling applications. If you want to try and understand what types of combinatorial objects you can use this on, one of the constraints that one finds fairly quickly is that these, I'm maybe lying a little bit, but that these are very closely related to combinatorial objects called matroids, which are another classical object in sort of combinatorial optimization. So on a relatively high level, matroids are a combinatorial attempt to model versions of independence. This includes, so the sort of fundamental examples are linear independence of vectors in a vector space, and cyclic independence of edges in a graph. Formally, a matroid, one can formulate them lots of different ways. One way is that you have a ground set, say of the numbers 1 through n, or the edges in a graph, and you are interested in a collection of subsets with some property, like the spanning trees of a graph, where if you have two such subsets and you have an element that's in one that's not in the other, you can make an exchange. And the result is also an element of your collection. So I have this exchange property, as do, for example, the spanning trees of a connected graph. And this exchange property guarantees that, for example, if you want to use the greedy algorithm to find your favorite such object, that you will always succeed. So for example, finding the min cost spanning tree in a graph is an example of something that you can solve using a greedy algorithm. And that's exactly because the spanning trees of a graph form the bases of a matroid. And there's lots of different combinatorial objects you can associate to matroids. I just wanted to list some of them. Feel free to ignore this if you like. But the one thing you can associate to it is a simplicial complex, which is a collection of subsets that's closed under inclusion, like this one, or as showed up in Arit Dinner's talk, like a graph, but where we allow subsets of more than two things. And another very natural object to associate to matroids is a polytope, which is going to be the convex hull of a bunch of indicator vectors of these subsets. And so matroids have been around for a long time, but recently, especially in combinatorics and algebraic combinatorics, there have been some breakthroughs on the theory of matroids. And in particular, one of the big breakthroughs that happened was in 2015, where Karima Deprosito, Jin He, and Eric Katz wrote a beautiful, long, intense paper on what's called the Hodge theory for combinatorial geometries. Combinatorial geometries is another word for matroids, where they used techniques from algebraic geometry to associate complicated rings to these combinatorial objects and use them to get interesting consequences. In particular, something about the face numbers of this independence complex. And in particular, one October morning in the fall of 2017, Jin He came to MSRI and gave a talk on this work. And in particular, it's very small, but the talk that he gave was on negative correlation and the Hodge-Riemann relations, in which he discussed applications of this theory to negative correlation, which is related to negative dependence in matroids. And so this was really this was very closely related to things that were already going on down the hill at the Simons Institute, and started off this project of using this theory to develop implications for sampling and counting in matroids. And as with stable polynomials, the useful thing to do turned out to be to associate a class of polynomials with some property, with some functional property, to combinatorial objects and use those functional properties to say something about this distribution you're interested in. The functional property that came out of this work is log-concavity. So the property of interest for some polynomial with real coefficients, let's say non-negative, is that as a function on the positive orthant, log of f is concave. It's negative semi-definite Hessian. Okay, that's something. And stable polynomials, one can check, just like for the univariate example, have this property. So we get all of the things we had before. And we get a lot of the same consequences as we had before. So these were studied by Leonid Gurdjieff, who showed that log concavity of polynomials, again, gives you things like Newton's inequalities. So it tells you about the shape of your coefficients. And using this theory of Deprosito, Hu, and Katz, we were able to show that actually if you take any matroid whatsoever and you look at the basis generating polynomial, just like we had for spanning trees of this graph before, that this polynomial has this property of being log concave as a function on the positive orthant. Around the same time, many people were trying to simplify this complicated theory of Adapacito and Katz. So in particular, Peter Brendan and Jinhe also developed an equivalent class of polynomials they called Lorentzian polynomials with a lot of the same applications and same connections. How are you doing on time? Sorry, I should have brought a. Okay, well, we'll see. 5 minutes left. Okay, let's skip some stuff. So one consequence, well, okay, the high level of some slide is if you actually write down the consequences for log concavity, what ends up being important are the second largest eigenvalues of some matrix. One can translate this just by, again, the multivariate formula for what it means to be log concave into something about second largest eigenvalues of some matrices given by your combinatorial object. One consequence of this just is that one can recover Newton's inequalities, but for independent sets of matroids. So for example, if I look at all of the forests in a graph, acyclic subsets of edges, and order them, count the number with each number of edges, this sequence divided by the binomial coefficients is going to form a log concave sequence. It's going to satisfy all of these inequalities. That is one consequence of this, and comes out from the log concavity of a polynomial associated to these independent sets. One of the other very surprising connections that happened with this class of functions was actually a connection to Arit Dener's talk yesterday on what's called high dimensional expanders, random walks on faces of a simplicial complex. Which I'm not going to go into too much of the details on, but so this builds on a long line of work that some of which we saw in the talk yesterday on high dimensional expanders. And at a high level, what this is that we're going to be walking around on subsets of elements of a given size. And we're going to be walking around in a fairly natural way if we have some subset like these blue dots among the 7 dots. We can drop an element with some probability to get 3 and then add 1 back in with some probability. And if we take 2 steps of this walk, we get back to something of the original size. And so we can consider this as a random walk on, for example, subsets of size 4 of my 7 dots. And similarly, if I started at the bottom of this picture, started with something with 3 elements and added something in with some probability, and then deleted 1 again, then I would go from something with 3 elements to something of 3 elements. And so I would also get a random walk on these subsets of size 1 less. And part of the remarkable theory about this work is, so we get some random walks on these sets this way. And we might have many different levels in this picture, might have subsets of many different sizes. And the remarkable part of this theory is that one can bound eigenvalues of transition matrices from these walks, building up from small pieces and relate them all together. So in particular, work by Kaufman and Oppenheim showed that you can bound the eigenvalues of the giant random walk on the largest subsets, which could be quite large, and choose D, in terms of the eigenvalues of walks on just links of this simplicial complex, which one should think of as small local pieces of this simplicial complex. They call these lambda local spectral expanders because you're bounding spectral because you're bounding eigenvalues transition matrices, and local because you're doing that on small pieces of your simplicial complex. And they show that you can, the theorem is that you can use very local information to get global bounds on transition times. And one piece of the story I'm still sort of surprised by is that when we were understanding, part of the story of showing log concavity of matroid polynomials was characterizing polynomials with this property. And it turned out to match exactly with the characterization that they give. So in fact, the independence complex of any matroid is a 0 local spectral expander, so satisfies this condition. And in fact, one can use that to show many things, but in particular, for example, that the edge graph of the 0, 1 polytope I told you about before has certain expansion at least 1. Probably were, yeah, okay. So this has several consequences. Maybe I'll run through them and not worry too much about the details. But so consequences of this include that the bases of a matroid, for example, spanning trees of a graph, one can bound the mixing time of this random walk that you get on them in terms of the rank and the number of elements. This has been improved since then, and now the bound is down to O of R log R. These bounds are about the mixing time of random walk. So in particular, it doesn't say anything about the complexity of taking a step. But if you run this, for example, to sample a spanning tree of a graph, approximately uniformly at random, this gives, as far as I know, this gives one of the best running times for sampling spanning trees from graphs. So just since it's been a lot of details, for example, if we wanted to, here's a grid graph, if we wanted to sample spanning trees, the algorithm is to add an edge rather than delete one, and then find the set of edges that we could delete to get back to a spanning tree, which is a cycle, and then delete one and keep going. And so what this does is this defines a random walk in the space of spanning trees. And the guarantee is that this random walk mixes quickly. And so if you wanted a random spanning tree, you could run this for some number of iterations, and then at the end, you have something that's about uniform. Okay, so since then, there's been a lot of work. I apologize for the incomplete list, but there's been a lot of work on understanding other properties of distributions and polynomials that will have algorithmic implications for sampling like this. So spectral, yeah, there's a list for those of you who are interested. But I think it's been a very fruitful connection between people in mathematics like combinatorics and convex analysis, and people in theoretical computer science with sampling algorithms. And I think so we sort of, this story was really one about matroids, and I think moving forward, we're going to see what other sort of combinatorial objects this theory can tackle. So I will stop there, and thanks for your time.
See the amount of work that has come up in such a short amount of time. Are there any questions? I think everybody's ready for lunch, for a break. Thank you very much. Thanks.